Now, let's continue our discussion about numerical integration. So far, you already know about two methods to integrate numerically. The first one is called trapezoidal rule, and the second one is called one-third Simpson rule. And these two methods actually is used or can be used to evaluate the definite integral of fx from a to b. And now we want to discuss a method that is very powerful to evaluate the same definite integral, which is to integrate fx with respect to x from a to b. And this method is called Gauss quadrature. In this method, or the general idea of this method is, instead of evaluate our integral from a to b, or evaluate our function from a to b, and now we need to evaluate the function, our function from -1 to 1, or in general speaking, we need to transform our lower limit and also upper limit to be -1 and 1, and therefore our function fx also will be transformed to another kind of function. That is the general idea about Gauss quadrature. And therefore, if we have a definite integral from a to b for a function of x with respect to x, we need to evaluate this integral from -1 to 1 given a new transform function in terms of t with respect to t. So if you see here, what we need to have is a transformation formula from x become t, so that you can use this formula, or I think you need to remember this formula for this transformation formula from x to t. Here is a, on the left hand side here is a x domain, and then you need to transform your function to be in t domain by using this transformation formula. X is equal to b minus a multiplied by t plus b plus a. All of these divided by 2. And if you see here, in our original integration, in our original integral, we have dx. And from this transformation formula, we also can find our dx dt, which is b minus a upon by 2, so that this also implies our dx is equal to b minus a divided by 2 multiplied by dt. Thus, by using this transformation formula, we now transform our integral from x to t, and our lower limit and upper limit is -1 and 1 respectively. And upon the derivation from by using the transformation formula and some other algebraic manipulation, we can arrive at two formula if we are using 2-point Gauss quadrature, and if we use 3 points Gauss quadrature. And actually you can find in any reference book how to derive this formula, so that this on the left hand side, if you look at it at the 2 points Gauss quadrature, if we have, or if we want to integrate a function of x with respect to x from a to b by using Gauss quadrature, and by using our transformation formula, our function now is transformed, become like this, from -1 to 1, and we integrate our function gt with respect to t, and this is the formula. G -1 upon sec3 plus G 1 upon sec3. And by looking at this formula, the key point is we need to find our GT. What is our GT? So that after we find what is our GT, and then the next step is we just substitute our value of T is equal to -1 upon sec3 and 1 upon sec3. And it is same. If we are using 3 points Gauss quadrature, this is the formula that we will have. And we need to use this formula to evaluate this definite integral from a to b. And then now let's look at the example. How can we apply these two formula to evaluate our integral? So in this example 5, given integral I is equal to sin x upon x with respect to x, and the interval of integral is from 0 to 1, and then we need to use 2-point Gauss quadrature formula. If we do here this example 5 solution, example 5, what we want to evaluate is the integral from 0 to 1 of sin x divided by x dx. And what we have in a 2-point Gauss quadrature formula is integral from a to b fx dx is equal to -1 to 1 gt dt is approximately g 1 upon sec3 plus g -1 upon sec3. So by comparing the first term on the left hand side here with our question, what we have is our a now is 0, our b is 1, and our fx is sin x over x. And the key point, or the main important that we need to do, or that we need to use Gauss quadrature formula, is transformation of our x by using the formula that we know. And by using the formula that we know, our x, so here the first step is a transformation is equal to x is equal to b minus a multiplied by t plus b plus a divided by 2. And then what you can do, you just substitute 1 minus 0 is 1, t, and then plus 1 divided by 2. Here is our x. That implies our dx dt is equal to 1 upon 2. This also implies our dx is equal to 1 over 2 dt. Therefore, our definite integral now is from 0 to 1 sine x divided by x dx now becomes from negative 1 to 1 sine x, where our x now is t plus 1 divided by 2 divided by t plus 1 divided by 2, and our dx is equal to 1 upon 2 dt. And if you see here, we also can cancel out these 2 and 2, so that our integral now becomes from negative 1 to 1 sine t plus 1 divided by 2 divided by t plus 1 with respect to t. Now, we know that from this transformation, we can know that here is our gt, or our function of t. So again, going back to our 2 points Gauss quadrature formula, we can write our gt is equal to sine t plus 1 divided by 2 divided by t plus 1. And what we need to know is the value of this function gt when t is equal to 1 upon sed 3 and also negative 1 upon sed 3. So that the next step is you just substitute the value of t is equal to sed 3. So here we have sine 1 upon sed 3 plus 1 divided by 2 over 1 upon sed 3 plus 1. And if you substitute in the calculator, and don't forget your mode, because here is a trigo, so that we need to change our mode into radian, and what you will get is, for this one, the value is 0.4963 if we are using 4 decimal places. Oh, no. This is the value for negative. So for positive is 0.4498. And the next step, we also need g, the value of our function when t is equal to negative 1 upon sed 3, so that you just again just substitute the value in your calculator. So you don't need to do like this. Actually, just substitute your x value or any value into the equation in calculator, and what you will get for this one is equal to 0.4963. Therefore, by Gauss quadrature, this integral from 0 to 1 sine x upon x dx is equal to 0.4498 plus 0.4963, and what you will get is 0.9461. This is the value that you will get by using 2-point Gauss quadrature formula. So this is the solution for example 5. So for example 6, evaluate the integral of sin x over x cubed minus 1 with respect to x from 1 to 2 by using 3 points Gauss quadrature. And you can use the same procedure but now by using 3-point Gauss quadrature formula. And here is your answer. And let's take this example 6 as your exercise for today class. So maybe I should write here exercise. That you need to submit tonight. We have done for this example, but now let's look at some more example about Gauss quadrature. So now let's say this extra example. Let's say we want to use 3-point Gauss quadrature. Use 3-point Gauss quadrature. To approximate or to evaluate the integral I from 1 to 2 to x plus 3 over x squared dx. So as you know, we need to use, here in this example, we need to use 3 points Gauss quadrature. And if you look at in the formula of 3-point Gauss quadrature, I is equal to from a to b of fx, dx also is equal to from -1 to 1, gt with respect to t, approximately 5 upon 9, g negative third 3 upon 5 plus x over 9 g 0 plus 5 over 9 g negative third 3 over 5. For this example, again it is same like what we discussed just now by using 2 points formula. So the important thing is we need to find what is our function g here. And we can find it by using, the first step is by using the transformation. So here we can have a transformation formula. X equal to b minus a t plus b plus a divided by 2, and our b now is 2. 2 minus 1 is 1 plus 3 divided by 2. So here is our x, and we also can find dx dt is equal to 1 upon 2, so that our dx is equal to 1 upon 2 dt. And then the next step is you just substitute everything. You have what is your function of x, and you also already have, or you already know what is your dx. So this implies that integration from 1 to 2 of 2x plus 3 upon x squared dx is equal to integration from -1 to 1, 2, where our x now is 3 plus t plus 3 divided by 2 plus 3 over t plus 3 divided by 2. So this is square, and our dx is half dt. And 2 and 2 here, you can cancel it. And this one also is equal to negative 1 to 1. And then half multiplied by 3 plus t plus 3 over t plus 3 divided by 2 square dt. So by looking at this integral after transformation of a coordinate, we know that this one is our gt. So you can write here your gt is equal to half multiplied by 3 plus t plus 3 divided by t plus 3 divided by 2 square. And if we want to use the 3-point Gauss quadrature, we need to have these three values. What is a g when t is equal to negative sed 3 upon 5, when t equal to 0, and also when t is equal to negative sed 3 upon 5. So you just need to substitute 3 upon 5 equal to what? And g0 equal to what? You can use this one by using your calculator. And when t is equal to negative sed 3 upon 5. So for this one, for the first one, when t is equal to sed 3 upon 5 is 14.3872. You should get this one. And when t equal to 0, you'll get 12.5. And when t is equal to negative sed 3 upon 5, you will get 12.1108 if you are taking 4 decimal places. And then now if you want to use the formula of 3-point is 3-point Gauss quadrature is equal to, or your integral is equal to 5 over 9 multiplied by 12.1108, then plus 8 over 9 multiplied by 12.5 plus 5 over 9 multiplied by 14.3872. And if you sum up all of these, what you will get is 25.8322. So this is our answer of numerical integration by using 3 points Gauss quadrature formula. Actually, you also can try by using 2 points formula. 2-point formula. It is the same function, but what you need to do is just change what is your value of t. Now for 2-point, your value of t is 1 upon sed 3 and also negative 1 upon sed 3. And if you try, and then what you will get is here is 13.8052, and for this one, the next one is 12.0015, and the answer for this integral by using 2 points Gauss quadrature, you will get 25.8067. So if you see here, there's a little bit different between 2 points and 3 points. And how to know what is the error between, or what is the difference between 3 points and 2 points? So for this integral, actually you can find what is the value of this integral exactly analytically. Analytically, you can try by yourself, because here you can integrate as usual. Analytically, this I is equal to 23 point, not 23, it's a 25.8333 if we are using 4 decimal places. And then now we can see, or we can look at what is the error between 2 points and 3 points. So of course the error here for this 3 point is the error, or the absolute error, is equal to 25.8333 minus 25.8322 is about 0.0011, and while for the 2 point, the error is 25.83333 minus 25.8067, and for this one you will get 0.0266. So this is the difference between 2 points and 3 points. And if you see here, the more point that we use, and the error is a little very small, very tiny error, where this error is about 0.005% error only, while for the 2 point it's about 0.1 error, 0.1%, 0.103% error.